For this part, we're going to talk about how we can use this idea of a normal distribution model as well as z-scores together to understand what's going on in the world around us. So we can use z-scores in the context of a standard normal distribution model in several respects. First of all, we can compare values from two or more variables that we think are normally distributed, yet are on two different scales. So for example, you might compare exam scores. The SAT and the ACT are both popular exams administered in the United States, but they're on different scales even though they're normally distributed. So we can use z-scores to compare different values based on SAT and ACT scores. We can also find probabilities of particular values from a normally distributed numerical variable. So for example, you might find the probability of a particular range of SAT scores. You can also find percentiles. Given a particular raw value and a corresponding z-score of a numerical variable that we know is normally distributed, we can find a particular percentile. So you might find the percentile of an SAT score of 1800, given that you know its z-score is 1. So let's go through a couple of these examples. The SAT, it was originally called the Scholastic Achievement Test, and the ACT, again, it was originally referring to this group called American College Testing. These are both standardized tests for admission into higher education in the United States. They're both normally distributed, or nearly normal, in the population. And suppose that we know that the mean of the SAT score is 1500 and the standard deviation is 300. And for the ACT, the mean is 21 and the standard deviation is 5. This is both in the population. Well, suppose we know these facts. If we're told a particular person, let's call her Anne, scored 1800 on her SAT, and another person, Tom, scored 24 on his ACT, who performed better? These are two different values on two different scales. The problem is that if you look at the raw score, Anne scored much better than Tom, okay? Because Anne scores 1800, Tom scores is 24. So you think, oh, well, Anne scored much better, obviously. But keep in mind, they're on different scales. They have different means and different spreads. So let's compare Anne versus Tom. What we can do is we can convert Anne and Tom's scores into standardized scores, or z-scores. And then we can compare their z-scores. Keep in mind, a z-score, just a standardized score. You can think of it as the number of standard deviations above or below the mean. So for Anne, we standardize her score by removing the mean for the population and divide by the standard deviation for the population. So she took the SAT score, so we divide the mean of the SAT, which is 1500, and we divide by the standard deviation of the SAT. And so she has a z-score of 1. That means her score of 1800 on the SAT is 1 standard deviation above the mean in the population for all SAT takers. For Tom, when we convert his raw score into a standardized score, or z-score, we subtract out the mean for ACT and divide by the standard deviation for ACT. So we take 24 minus 21 and divide by 5, and we get a standard score of 0.6. That's a z-score. So you can see that Anne scored relatively better than Tom, because Tom is about 0.6 standard deviations above the mean, whereas Anne is about 1 standard deviation above the mean. So Anne scored relatively better than Tom. We can also use their z-scores, and since we know both of the distributions in the population for SAT and ACT scores, they're both normal, we can use a standard normal distribution model and plot their scores to see how they're doing. So for example, in this top plot, right, that model is roughly the distribution for SAT takers. And you can see that Anne gets a z-score of about 1, and Tom gets a z-score of about 0.6. So Anne scored relatively better than Tom. As well, you can use z-scores in the standard normal distribution model to find probabilities. Keep in mind, a standard normal distribution model, or the normal distribution model more generally, it is a probability distribution. So if we know certain values, right, we can find probabilities of obtaining those particular set of values. So if we know a z-score and we know the distribution is normal, we can use the standard normal distribution model to find probabilities within a given range. So historically, people have used normal probability tables rather than statistical software to find these probabilities. That's because statistical software really wasn't widely available until very recently. We will focus for this course on using statistical software because with statistical software, we can focus more on understanding what's going on rather than some of the tedious aspects of finding probabilities within tables. However, we will still, for this purpose right now, we will talk a little bit about normal probability tables just so that you know, because if you encounter a normal probability table, you see what's going on. But in general, we really prefer statistical software. It's how most researchers actually find probabilities, given a z-score and knowing something about the distribution being normal. So how do we find probabilities from z-scores? Well, we know Anne earned a score of 1800 on her SAT, and she has a z-score of 1. So her SAT score of 1800 is 1 standard deviation above the mean of all SAT takers. Let's suppose Dave took the SAT test, and we don't know his score, right? Well, if we know that in the population, the average for the SAT is 1500, and the standard deviation in the population is 300, then we might ask, what is the probability that Dave scored equal to or lower than Anne? Right? We might ask, in terms of notation, what is the probability of obtaining a z-score less than or equal to Anne's z-score? Right? We use capital Z to refer to a range of z-scores, and lowercase z to refer to a particular z-score that we want to use as a benchmark. And in this case, P, it just refers to probability. So we're finding the probability of finding a z-score equal to or less than Anne's z-score. So we will first use statistical software, and then we're going to show how to do this using a normal probability table. So finding probability with statistical software is really quite easy. In this case, you can see that we've chunked off, right, the standard normal distribution based on Anne's test score. So you have Anne's test score in terms of a z-score. She scored 1 standard deviation above the mean. And you can see that the bulk of the probability, all right, it's in the left-hand side. And then the area of the, to the right of Anne is quite a bit smaller, okay? You can also find this probability using a table, right? The probability of obtaining a z-score less than that benchmark is about 0.841. When you use a normal probability table, the first decimal place is typically in the rows, while the second decimal place is listed in the columns. And each cell gives the probability, by convention, below a certain z-score. Okay? It gives you the probability of having a z-score below some cutoff z-score. So in this case, that cutoff is Anne's z-score of 1. So we might say, well, what's the probability of a z-score less than 1? Right? We go down to that row equal to 1, and since that decimal place, that second decimal place, is in fact 0, okay, we in fact have this probability of 0.841. And if we want to find the probability of z being greater than or equal to 1, which is where 1 is Anne's z-score, we just use the complement rule. Right? We just subtract 0.841 from 1, and we get this probability of 0.159. So the probability of obtaining a z-score greater than or equal to Anne's is about 15.9% or 0.159, and the probability of obtaining a z-score less than Anne's is 0.841 or 84.1%. So you can see that Anne scored quite well on the SAT takers. We'd expect most people, roughly 84.1% of people, to have actually scored below her. And we can compare these two approaches using statistical software and probability tables. Now, one thing I really like about statistical software is you can visualize the distribution. It's a good reminder that these probabilities are based on areas under a curve. And that curve is denoted by the standard normal distribution model. You can see that that light blue area is just a larger chunk of that overall distribution. That reflects the fact that the probability of obtaining a z-score less than Anne's or equal to Anne's is 0.841. Right? Now, there's an important note on output. Okay? There's some variation depending on the statistical software you use, and even across different normal probability tables. Okay? For example, in this example, the normal probability table, it gives you the probability of having a z-score below a certain cutoff value, while the statistical software is giving you the probability of having a z-score less than or equal to a particular value. Now, these differences are really rarely that important in a practical sense. So for this course, we will focus on treating these as roughly equivalent quantities. We will typically use this equivalency sign, or this approximately equal sign, to denote that we are obtaining very close approximate probabilities. So just to really hammer this home, we're just going to say, well, the probability of having a z-score less than a particular cutoff value is roughly equal to the probability of having a z-score less than or equal to a particular cutoff value. So you can see these probabilities are really more or less equivalent. Right? So I don't want you to get hung up on these small differences. We're going to focus on obtaining approximate equalities. And similarly, you can see that there's a slight difference in what the statistical software gives you and the normal probability table gives you. But in fact, they're so close that we're going to treat these as approximately equal. Now there's another issue, is that with probabilities you can treat them as percentiles, as we've alluded to previously. So we know Anne earned a score of 1800 on the SAT, and her z-score is 1. So she scored 1 standard deviation above the mean of all SAT takers. Well, we know the mean of the SAT is 1500 and the standard deviation is 300 in the population. So you might say, what is her percentile among all SAT takers? Well, if you recall, a percentile is simply the percentage of people who earned a lower score than she did. So this is equivalent to finding the probability of having a z-score less than Anne's. So the percentile, we can just find the probability of obtaining a z-score less than Anne's. Now the normal probability table in this example is going to give you the probability less than Anne's, which is 0.841. The statistical software is going to give you the probability of having a z-score less than or equal to Anne's, but it's, in any practical sense, it's equivalent. So for this course, we're treating these as equivalent, and you can see that Anne's percentile is about 84.1%. So roughly 84.1% of all SAT takers scored lower than she did. Tables versus statistical software is an important distinction. Historically, people have used tables to find probabilities. That's because they didn't have computers. But we will focus on using statistical software. There's no reason not to use statistical software, except that occasionally you'll encounter probability tables. It's important to understand them. But we like statistical software because it emphasizes visualization. It emphasizes the fact that these probabilities are not coming from nowhere. They're in fact coming from a normal distribution model. As a reminder about tables versus statistical software, historically people have used tables to find probabilities. That's because computers weren't widely available. But we will focus on using statistical software. There isn't really good reason to prefer tables over statistical software unless your computer breaks down. Because with statistical software, it's obvious with visualization that these probabilities, they're not coming from the ether. They're in fact coming from a normal distribution model. In fact, the standard normal distribution model in the case of z-scores. Let's go through a few more examples to really understand what's going on. So let's talk about Shannon. She's a randomly selected SAT taker. We don't know anything about her SAT aptitude. We might say, what is the probability that Shannon scores at least 1630 on her SATs? Well, we know the SAT scores are normally distributed in the population with a mean of 1500 and a standard deviation of 300. We can first calculate the z-score for scoring 1630, because we're saying, what's the probability that Shannon scores 1630 or greater, at least 1630, that's what that means. So we convert her value to a z-score, or this cutoff to a z-score. We take 1630 minus 1500 divided by 300. We get this z-score of 0.43. That is 0.43 standard deviations above the mean of all SAT takers. This is what these probabilities look in terms of statistical software. So the z-score there is 0.43. You can see we've chunked off the upper and lower half. Right? The area under the curve to the left has a certain probability, and the area to the curve to the right has a certain probability. With the area to the left, it's more likely that you randomly select a person from that part of the distribution because it's a larger area under the curve. Right? We can also find probabilities with a table. So in this table, by convention, it gives you the probability below a certain z-score. So accordingly, with a z of 0.43, we can find the probability of a z-score below 0.43 is, in fact, 0.666, right? To find the probability of some z-score greater than or equal to 0.66, we can just use the complement rule. Okay? The entire area under the distribution has a probability of 1. We subtract out the probability of having a z-score less than 0.43. We get the probability of having a z-score greater than equal to 0.43, and that probability is about 1 in 3. Right? And this is just based on that normal probability table. So we can conclude that the probability of Shannon scoring at least 1630 on our SAT exam is about 1 in 3, right? 0.334. Note that this requires us to know that the population distribution can be approximated by the normal model with a known mean and a standard deviation. Right? That's the important part about Shannon. And with that, we will go through a few more examples about working with z-scores and the standard normal distribution model.